Right, so let's get started. So we were talking about view modifications and how it wasn't straightforward to figure out what the modifications to a view meant for the underlying base relation. So that was, in some sense, a conundrum that we were in. And we had this example where a view was constructed from this relation cells under these conditions: bar is equal to Joe bar or bar is equal to Mo bar, and then depending on which attributes you ended up selecting, it was either straightforward or not straightforward to push an update into the view, which is Joe Mo bar cells, into the underlying relation. And eventually we had this set of rules that allowed us to tell whether we can do a particular update or not. So the rules include the first clause, which is that the view must have been defined using a selection on some attributes from one relation R. The where clause must not involve R again as a subquery, and the select list must include every attribute for which you can't assign null as a default value. Because if you can't assign null as a default value for that attribute, then you have to fill that attribute with something, right? And if the view does not select that attribute, then you don't know what that value needs to be filled in with. Okay, so in some sense, this condition allows you to, in some sense, because you are subselecting a set of attributes in your view, if an attribute is missing from that set of attributes, then it should be something you can assign null to. Okay, so and like I said, these rules are quite conservative, and even when an update is allowed, it might not work as you would expect. So let's quickly look at two examples, and then that'll be sort of the end of this topic. So let's say I have an aggregation, right? So I have select sum of salary from employees where age is greater than 30. So let's say I decide to do an update to the view, and I say, you know what, instead of sum of salary being 3,500, let's change it to 3,575. Okay? So why is this not straightforward to translate back into the base relation? Why would it not be easy to do that? Yep. So you're changing the, yes, you're right. So you're changing the sum, which is the aggregate, and you're not changing individual salary. So the way to think about this is, let's say this is the result of the view. This result is computed by summing up all of the individual salaries of all of the employees where age is greater than 50. So if you have an update to this value, you don't know how to attribute it to any of these ones, all of which whose age is greater than 50. Firstly, you don't know what their age is because you only have made an update to salary. And secondly, you don't know their identities because you don't know which of these tuples you should update. Okay, so basically, changes of this form should be disallowed. You should say, look, that is not allowed. Let's take another example. So this is simpler, which is with cells being bar, beer, and price. Let's say I have a view which is select beer, comma, price from cells where bar is equal to Joe bar. Why is this straightforward? Why is this allowed according to the rules that we saw earlier and intuitively? So let's say I wanted to add a new beer, comma, price to this relation, or update an existing one from this relation, where this relation, by this relation I mean the view. Why is that straightforward? So the reason why it's straightforward is, unlike this case, where if you see it's like a kind of a many-to-one kind of a mapping, here it is a one-to-one, right? So the way to think about this is, let's say these are the results of your view, these are the base relation, base table tuples, each one of these tuples maps to exactly 1 in your output. Okay? Of course, some of them may not map to anything in the output because they are not Joe bar, but let's say these are all Joe bar tuples. Good so far? So if you make a change to any one of these, then I know which one to modify. I can translate it back to the original tuple. Yes? Make sense? Okay. So that's sort of two extreme cases for why it may be either hard or easy to translate modifications on the view back to the base relation. In general, it's a very complicated problem. There are no sort of, even though there's a lot of research on this problem, it's often still a topic of research. Okay? So let's move on. The last topic that I wanted to cover within the view definition space was the notion of materialized views. So far, we've been talking about virtual views. So these views are defined, but you don't actually create them. You don't really materialize their result. You don't create a new relation with the result. So as you get queries on the virtual table, you translate that into queries on the base relation. So that's what has happened so far. Instead, another option is to actually materialize it. So a materialized view is one that is actually stored instead of simply storing the query. So as in traditional views, which are nothing but virtual tables. Right? So in this case, when you say create materialized view as blah, 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 it becomes actually stored. It becomes stored. So there are pros and cons to this. The pro is that you've already created the query result. You've already created the view result. So if someone says, give me all of the results from this view, you've already computed it. You don't need to do any additional work. On the other hand, it is problematic because you need to keep this view up to date as the results change. So think about it in the following way. So let's say this is a materialized view, and this is gotten from this underlying relation R. If I go and update or delete some tuples from R, then I have to go and do that for the materialized view as well, because otherwise the view would be stale, right? Otherwise the view would no longer be an actual view of this relation. It would be a stale view. On the other hand, if it was virtual, then I don't need to make any change because I don't store the result. I only store the query, right? So in the materialized view case, I'm storing both the view result and the relation. In the virtual table case, I'm storing the base relation, of course, and this query. I'm not storing the result. Okay? Any questions about this? Okay. So one last note here is that if the base table, if the relation R does not change it as much, then it's probably okay to store something as a materialized view because you don't need to update it that much, right? So there are pros and cons. If you have a lot of updates, then it's probably not a good idea to store a materialized view. If you have relatively few updates and you repeatedly query this view, then it's probably a good idea to store it as a materialized view. Okay? So that's it with views. Let's move on to our next topic. Guess I can't do that. Okay. No. Okay, so our next topic is constraints and triggers. This is the last SQL topic that we are going to be covering. It's actually a very different style of SQL than you've been looking at so far. These are all focused on ensuring that your database meets certain desired properties. Okay, so that's the overall goal of constraints and triggers. So like I said, they are used to make sure that the data in your database makes sense. Some real-world properties are kept valid as queries and modifications are issued to your data. There are two types of ways you can do this. You can do this via constraints. These you can think of as assertions. Once again, the database needs to continuously maintain the fact that these assertions hold on the data. The second way is via these special commands, which are called triggers. These are very special commands that allow you to do certain kinds of bookkeeping. One way I like to think about assertions and triggers, or the difference between them, is that, or constraints and triggers, the difference between them is that constraints are more passive, they are less action-oriented, triggers are much more action-oriented. So that's the way I try to conceptually make a difference. But that said, constraints can also block or trigger certain actions, and triggers can also check certain constraints. So it's a little confusing, and the difference will become clearer as we go along. Okay, so let's start with one-line definition of both, and then we'll dive into constraints. So constraint is a relationship among data elements the DBMS, or database management system, is required to enforce. A key constraint is one example of a very simple type of constraint. Triggers, on the other hand, are very action-oriented. They are executed when a specified condition occurs. So if you insert a tuple to a certain relation, that might cause a certain action to take place. Okay? The other important thing to know here is that triggers are easier to implement than constraints. Often it's hard for you to figure out when to check your constraint, but for triggers it's easier because it's clearly defined that, hey, if you insert on this, do this. If you delete on this, do that. Right? So it's more action-oriented, and these are easier to check than constraints, at least the most general form of constraint that we'll study. Okay? All right, so we've seen one simple form of constraint, which is keys. Another form of constraint which is very closely related are foreign keys or referential integrity constraints, and we'll cover that in a second. Then you have increasingly sort of complicated forms of constraints. The first is a value-based constraint, which is constraining a single value of an attribute. Tuple-based constraints, which is constraining the relationship between components of a tuple. And general assertions, which could constrain values across relations, across tuples. This is fairly general and powerful. So let's start with foreign keys. We know what keys are, so let's start with foreign keys. So let's say you have a relation cells, which contains bar, beer, and price. The key property, or the constraint that we want to enforce, is that a beer that appears in this relation is something that is a real beer. Okay, it also appears in the beers relation. Okay, so in some sense this is saying that, look, the beer value here must appear in the beers relation. Or manufacturer, I think, I forget. Okay, so this beer value must be a real beer. It must appear in the beers relation under the value name. Okay, so a constraint that requires a beer in cells to be a beer in beers is called a foreign key constraint. Okay, it's not a key because it's not just about this relation, but it's a foreign key because it's saying something about another relation. Okay, so that's a way to think about this. So the way to define a foreign key is using the keyword references along with the keyword foreign key. So you can either have foreign key within the declaration of an attribute when only one attribute is involved, or as an element of the schema. So this is once again very much like primary key and unique, right? So you've seen the definition of primary key and unique, and if you had a primary key or unique on a single attribute, you list it as part of that attribute. If it is across multiple attributes, you list it as part of the schema, as at the end of the list of attributes. Okay, so this is just like that. So you either have it within the declaration of an attribute when only one attribute is involved, or as an element of the schema where you say, and the way to do it is foreign key, blah, references, relation, and then parentheses attributes. Okay, so this is the syntax. One thing to remember is that the attribute that you are referencing, so you have cells that is referencing beers, and in particular the cells.beer is referencing beers.name. So the referenced attribute beers.name must be declared as either primary key or unique in the beers relation. Why is that? Why does that make sense? Any guesses? Why should the referenced attribute be primary key or unique? So think of what this functionality or this type of constraint is achieving. This type of constraint is ensuring that you are having a pointer from your referencing attribute to your referenced attribute. Okay, so a way to think about that is here you have, let's say, a tuple corresponding to bud. If you can see that, this tuple needs to point to a tuple in the beers relation, because in some sense it's dependent on that beers relation tuple. Once again, here you have a Miller tuple. This must point to one tuple in the beers relation such that that tuple, so the cells tuple is dependent on the beers tuple. Similarly, for this bud, yet another bud tuple would reference the same tuple in the beers relation. Now, for that to happen, the pointer should go to only one place, right? It needs to uniquely go to one place. So you can't have two separate tuples that have the same value of the attribute that you're pointing to. Okay, so that attribute needs to be a primary key or a unique, so that you can have a unique pointer to that tuple or that value of that attribute. Okay, the tuple and the attribute are equivalent because that attribute has a single value for each tuple. Okay, so you have the reason why we want to ensure that this referenced attribute is primary key or unique is so that you have a single pointer from the referencing relation or every tuple in the referencing relation to the referenced relation. Any questions about this? Yes?
So, if beers had more than one attribute as a primary key, like they both were part of a single key, then would cells have to reference both of those attributes, or could it reference only one of those?
So, so it would have to reference both.
Okay.
So you can't have a foreign key relationship with an attribute which is not a primary key or unique. So you can't reference part of a primary key or a unique pair, right? So it has to be one of them. Because you could still have multiple tuples that have the same value for that attribute. Any other questions about this? Okay, all right. So here's one instance of how you may do this. This is as part of the attribute list as opposed to part of the schema. Here I've declared the name of beers as primary key, and within cells I'm saying, you know what, have this beer reference this name, right? So you're saying that beer char 20 references beer in parenthesis name. Okay, it's fairly straightforward. It's just saying that these set of values need to derive from these set of values, and I need to be able to point precisely to one of them. Okay, one of those values in the beers relation. So the same thing can be enforced as an element of the schema, just like primary key and unique. So you can say foreign key beer references beer's parenthesis name. This is not necessary in this case. You can easily place this within the declaration of that attribute, but if you had multi-attribute foreign keys, this is the way to do it. Okay? Right. So let's talk about how these foreign keys are enforced. So for foreign key constraints, there are two types of operations that could lead to foreign key violations. The first type of operation is an insert. So let's once again define what R and S is. So R is the referencing relation. There's a pointer from R to S. So S is a referenced relation. So this is your cells and this is your beers. Okay? So the first type of constraint or first type of violation can happen when you have an insert or an update to R that introduces values that are not found in S. For instance, you have a tuple corresponding to bud. You decided to change that to buddy, let's say, which is not a beer. So that could be a problem, right? So it's no longer pointing to a beer in S. Similarly, you can go ahead and insert a new tuple with the beer value buddy, which is not a beer in S. So therefore, or in the beers relation, and therefore that causes a violation of the constraint. Okay, with me so far? Okay, so that's one possible violation. The other possible violation is if you make any changes to S. Okay, so if you make a change to S such that, let's say you go ahead and delete the Miller tuple. If you delete the Miller tuple, there may be some tuples in cells that are pointing to that Miller tuple. That becomes a violation now, right? Or if you go ahead and update the value of the Miller tuple to Miller Lite, once again that becomes a violation because at least in the cells relation, you've listed them as Miller as opposed to Miller Lite. Yes? Okay. So these are the two possible cases of violations. There are two other cases that we are not worried about, which are inserts to the referenced relation and deletion from the referencing relation. So why are these not important? Yep.
Well, for like the insert to S, it has like nothing being dependent on it yet, so it doesn't really matter if you like insert something.
Yep.
Also for deletion of R, it's like when you delete it, then like there's one less thing that depends on something in S.
Absolutely. So so she said if you are inserting something into the beers relation, so into S, then there's nothing really dependent on that, so that can't really cause any new violations. Similarly, if you delete something from R, right, so delete something from the cells relation, all that you're doing is removing some pointers to S. You're not really introducing any new pointers that may cause violations. You're just removing tuples. You can't introduce any new conflicts. Okay? So these cases are not important. The cases that we need to worry about are inserts and updates to R or deletions or updates to S. So once again, inserts or updates to R introduces values that are not found in S, causes a violation, and a deletion or updates to S. So maybe what I find to be helpful here is to think about these as two sets with or a bipartite graph, if you will, with edges between tuples from R to S. Okay, so that's one helpful way of visualizing what is going on. So an insert or an update to R introduces values that are not found in S. So let's say you add a new tuple in R, and that is trying to point to a value that's not found in S. This could cause a problem. Or a deletion or an updation to S causes some tuples in R to dangle. So let's say I changed the value of this tuple, I moved it here, let's say now this pointer is dangling, right? So this pointer is dangling and I need to fix it. Again, this is just a way of visualizing it. You can still reason about everything without visualizing. Okay, so what happens? What do you do when you have an insertion or a deletion to R, or an updation or insertion or insert or an update to R, deletion or an update to S? Okay, so what happens then? When you make any changes to the referencing relation, so referencing relation is R, then any insert or update to this referencing relation that introduces a non-existent beer, that must be rejected. Okay, so at least that's how for this type of violation is enforced for foreign key constraints. So it's just going to reject that. On the other hand, if there are changes to the referenced relation, then there are three ways you can handle this. Okay, so a deletion or updates to beers that removes a beer value found in some tuples of cells can be handled in three ways. There are three different ways you can handle that. And the reason why the first one just results in a reject while the second one there are many ways of handling it, is because the way to think about this is that there is R is a relation that is dependent on S. So if there are changes to S, we still want to be able to support that, but R is a weaker relation, so we are okay with rejecting some of the updates to R. At least that's the way foreign key constraints are handled right now. I'll tell you how we can handle this constraint or this violation in a better way later on. Okay, so for now, updates to R are rejected. Updates to S can be handled in three separate ways. Okay, so let's talk about those three ways. So the first way is the same as the way we talked about for updates to R, which is to reject the modification. Okay, so the default is you reject the modification. But there are two other ways that we can make these updates without rejecting the modification. So the first way to do that is to make the same changes in cells. Okay, so if there is a deleted beer, you delete the corresponding cells tuple. If there's an updated beer, you change the value in cells. Okay, so this is known as cascade. Okay, because the updates to S cascade back to R. So once again, if you think of R and S, you make any changes to S. Let's say you go ahead and delete a tuple in S, the corresponding tuples in R will get deleted. If you change a value in one of the tuples in S, then the values in the corresponding tuples in R also get updated. Okay, so that's what cascade means. Again, there are flavors of cascade. We'll get into that in a second. The last option is to set null. Okay, so if I make a change or I delete a tuple in S, the tuples that were dependent on it are their cells, their beer value is set to null. Okay, their beer value is set to null. That is a simpler option where you say, look, I don't really know what the value is because I was dependent on that tuple and that tuple's value changed, so I'm just going to set it as null. Okay? All right, so let's walk through how we might do this. So we've seen this example, but let me go through that once again. So if you have R and S where R is beers, R is cells and S is beers, and you delete the bud tuple from beers, then you go ahead and delete all the tuples from S that have beer is equal to bud. If you update the value of the bud tuple from bud to Budweiser, then you change all of the cells tuple with beer is equal to bud such that beer is now equal to Budweiser for those tuples. Okay? So that's what happens with cascade. Set null, like I said, is straightforward. If you delete the bud tuple from beers, you change all of the tuples of cells that have beer is equal to bud to beer is equal to null. If you update the value of the bud tuple by changing bud to Budweiser, you make the same change. You still say beer is equal to null for those tuples. Okay. So in deciding whether to do cascade or set null, remember the default is to always reject. So if you don't do cascade or set null, then it's going to be default, which is reject. And you can set these policies as either set null or cascade independently for deletions and updates to S, okay, which is a reference relation. The way to do this is to simply say on, and you say either update or delete, and then you say set null or cascade. Okay, so you can say on one of these two options, update and delete, and one of these two options, set null or cascade. Okay, so you can use two such clauses, one corresponding to update and one corresponding to delete. Otherwise, the default, which is reject, is going to be used. So here's an example. So in this case, I have the cells relation, once again, with the foreign key from beer to beers.name, right? So once again, it's a foreign key from cells to beer. And I'm saying on delete, you go ahead and set null, and on update, you cascade it. Okay? So let's consider a simple example, and let's walk through that. So you have, let's say, cells, and then beers, and let's say you have one tuple corresponding to Bud and one tuple corresponding to Miller. And let's say here you had a Bud tuple and a Miller tuple. Okay? So this says on delete set null. So let's say I go ahead and have an update statement to beer, and I say delete the tuple where beer is equal to Miller. If that happens, then what I would do is the database system would go to this relation. It'll change this value of Miller to null. Okay? What if you do an update instead? So instead of Bud, I changed Bud in the beer relation to Budweiser. Here, what would happen, or what the database system would do, is it would change both of these values to now be Budweiser. Okay? So that's how these constraints or these violations are handled on deletions and updations to the referenced relation, which is beer in this case. Any questions about this? Okay. There's one potential problem here, which is with the not null clause. Remember that this is one of the types of constraints that we mentioned way back when we were declaring schemas. When we say not null, this can interfere with some of the set null type update rules or ways of fixing the violations. And let's say you have on delete set null. This can cause a problem if that attribute is not allowed to be value null. So the way to fix this is to not have any constraints of this form. You can't have any clauses that allow you to set null, because there's no way this value can be set to null. Okay, so there is some interference between set null and not null, so that's obviously something that one should be careful about. Okay, so we've seen some attribute-based, rather we've seen two types of constraints, which are keys and foreign keys, and we've also seen set null, not null in the past. Let's talk about sort of very specific types of checks, which are attribute-based checks and tuple-based checks in a more general context. The ones that we've been talking about are very specialized. These are more general. The attribute-based ones target one attribute at a time. Tuple-based ones target more than one attribute at a time. So attribute-based checks allow you to place a constraint on the value of a specific attribute. You simply add a check and then in parentheses condition, and this is added to the declaration of that attribute. This condition may use the name of the attribute, but any other relation or attribute name must be within a subquery, okay, because this name of this attribute is uniquely determined by a tuple. Any other relation or attribute name is not supposed to be listed as part of that check. It must be within a subquery. So let's see what that means. Here I'm showing you attribute-based check which has roughly the same effect as a foreign key constraint. Okay, so here you have beer, which has is defined to be a char with 20 characters. Check, which is how you define an attribute-based constraint or a tuple-based constraint. Beer in select name from beers. Okay, so you're saying that, you know what, check that the beer value is among the beers in the beers relation. Okay, so this is achieving roughly the same effect as the foreign key constraint. We'll talk about the differences in a second. Another example is this constraint on price. Here I have a check that price has to be less than or equal to 5. Okay, so this is I'm ensuring at all times that the price of any tuples in this relation is less than or equal to 5. Okay? So now let's get back to this one and talk about how this differs or is similar to the foreign key constraint. So the key difference between this and the foreign key constraint is the timing of the enforcement. So when you list a check, an attribute check along with an attribute, that check is enforced or checked only when that attribute is updated. Okay, so it's not checked when, for example, the reference relation is updated. It's only checked when that attribute is updated. So, for example, if you have price is less than or equal to 5, this check is only checked when there's an update to price. So it checks if the new price is less than or equal to 5, and then it's rejected if it is greater than 5. Similarly, for this check beer in select name from beers, this is not checked if a beer is deleted from the beers relation or updated, unlike foreign keys, right? So unlike foreign keys, which do look at updates and deletions and inserts to both relations, this is only checked if that attribute is updated or modified, right? Updated or insert. Okay, so it's not checked for updates to the referenced relation. It's only checked for updates to the referencing relation. This clear? Tuple-based checks are more general. These are listed as part of the schema at the end of the list of attributes. They may refer to any attribute of the relation, but any other attributes or relations require a subquery. This is just like the condition for the attribute-based check. Very intuitive because you only want to refer to the things that you want to be checking as part of the clause. Everything else must be buried within a select statement or a subquery. Once again, these tuple-based checks are checked on inserts or updates to that relation. Okay, so these are checked on inserts or updates to that relation. So here's an example of a tuple-based check. Let's say I have a condition that only Joe Bar can sell beer for more than $5. I simply list a tuple-based check at the end saying bar is equal to Joe Bar or price is less than or equal to 5. Okay, so this is a general form of constraint. So why do we need a tuple level check when we can do an attribute-based check? The first reason is obvious. If a check requires more than one attribute of the tuple, we do need a tuple-based check. So the previous condition, for example, is something that required both attributes, so you can't place it as part of an attribute-based check. You have to place it as a tuple-based check. The second reason also is fairly straightforward. Tuple-based constraints are checked more frequently. Attribute-based checks are only checked when that particular attribute is changed. So if you have an attribute-based check corresponding to beer, only if that attribute is changed is that constraint checked. While in this case, if you have any inserts or updates to any of the concerned attributes in this tuple-based check, it is checked. Okay, so it's just more general. That's all that matters. Beyond checks or constraints that are listed along with one relation, you could also have checks or constraints listed across multiple relations. And the way to do that is via these assertions. You say create assertion name, check, and then parentheses condition. So the common thing here is this keyword check, which is common between tuple-based, attribute-based, as well as more general assertion-based constraints. These conditions can refer to any relation or attribute in the database schema. And this assertion or condition must be true at all times. So here's an example. Let's say I want to ensure in the cells relation that no bar may charge an average of more than $5. The way to do this is to create an assertion which is called something, let's say no rip-off bars, and a check condition. Within the check condition I have not exists, so saying that there does not exist anything within this subquery. The subquery is select bar from cells, group by bar, having average price is greater than 5. Okay? So this subquery here is listing all of the bars whose average price is greater than 5, and this not exist condition is checking if that relation is empty or not, and the overall condition is constantly ensuring that any updates happen to any of the relations, this condition is always met. So if there are any updates that violate this, it will say, sorry, you can't make that update. Okay? Any questions? Okay. So here's another example of an assertion, again a general form of constraint. Here I want to ensure that there can't be more bars than drinkers. The way to do this is to create assertion with some name, let's say few bar, check, and parentheses the condition, select count star from beers less than or equal to select count star from drinkers. Okay, so here I'm checking that the count of bars is always less than or equal to the count of drinkers. Okay, very straightforward. Pretty much any general condition involving subqueries and general sort of constructs that you'll use in conditions can be used within this assertion. Questions about this? Okay. So, so there's one issue here, which is it's not entirely clear when to check an assertion, right? So in principle, we want to be checking the assertion after every single modification to every single relation in the database. But you can do better, right? So a clever system can observe that only certain changes can cause an assertion to be violated. So let's say this is my assertion. Once again, it's few bar. I'm trying to check if the count of bars is less than or equal to the count of drinkers. Okay? So let's talk about these potential updates. Can a change to the relation beers affect whether or not few bar is violated? Yes? Why is that? You can insert into beers, but beers is not part of bars or drinkers. right? So since it's not part of bars or drinkers, these are three separate relations, it's not going to affect few bar, right? Few bar is only going to be affected if there are changes to bars or drinkers to begin with. What about a deletion to bars? Yes? So why do you think that?
Because now I'm doubting myself.
Anyone else? Yeah?
Because we are assert that the bars should be fewer than drinkers, so anti-deletion will only make the bars even fewer.
Correct. So you don't need to do it in this case, right? So the thing is, any deletion from bars is only going to make the count of tuples within bars even smaller. So no matter what deletion you do, you don't need to check this because the condition is going to continue to be true. On the other hand, an insertion into bars, you do need to check because that could cause a constraint to be valid, right? So there are, looking at this condition, it is very hard for a database system to figure out what types of modifications require you to check this constraint. So unfortunately, in most cases, these database systems end up checking these constraints almost all the time, except for trivial ones like this one, right? Do beers affect few bar? That's obviously false because beers is not listed here. So that's easy to check. But these more subtle ones, most database systems are not able to make up that distinction or make out that distinction, and therefore they would go and check for every single update to bars or drinkers. Okay? So, so this brings us to the motivation for triggers. So attribute and tuple-based checks have limited capabilities. Assertions are fairly general, but they are hard to implement efficiently. The database system must have real intelligence to avoid checking assertions that couldn't possibly be violated, like in the previous case, right? So here, a deletion from bars cannot violate the assertion, but this is something that the database system must have real intelligence to avoid checking assertions in that case. So triggers is the solution for that. So the triggers allow the user to explicitly specify when the constraint check occurs and explicitly specify what needs to be done to fix that violation. So like an assertion, a trigger has a general purpose condition, but also can perform any sequence of database modification statements. So triggers follow a fairly sort of powerful template. This is the ECA template, which is the event condition action template. So it starts off with an event. So this is a type of database modification, such as inserts on cells. Then there's a condition, so you check whether the insert has certain properties. So this can be any SQL Boolean valued expression. And then there's the action, which are SQL statements that are executed to fix the violation in some way. Okay? So let's get into an example. So there are many details to learn about triggers. Here's an example to set the stage. And the example is for this particular use case, which is with the foreign key constraint. Remember that I have, if I have an update or an insertion to cells, then I'm rejecting that. A deletion or an updation to beers is fixed, right? It's fixed via set, null, or cascade. But a deletion, an insertion or an updation to cells is rejected. That is the default behavior for foreign keys. That's not, there's no way to override that behavior. But a trigger can actually allow you to fix that. So in this case, we want to have a trigger such that if you have a new beer that is added to, let's say, the cells relation, then that same beer is added to the beers relation with null as the manufacturer. Okay, so let's say we want to do that. Make sense so far? Okay, so this is how a trigger looks like. It's fairly complicated, and this is the main reason why I allowed cheat sheets in the final or the second midterm. Okay, I cannot remember the syntax for this. So it's a lot to take in, but it's easier to do so once you break it up. Okay, so this is how it looks. It's like several lines. There are three parts that are easy to distinguish. The first part is the event, which is, in this case, after an insert on cells, right? So once again, what we want to do is, after an insert on cells, we want to insert the same thing into beers with manufacturer equals null. Okay, that's what we want to do. So this is the event, and then what would the check condition be, right? So the check condition is, if the tuple that you've added is not in the list of tuples in beers, then you need to add a tuple to beers, right? So that is the condition. Finally, you have the action. The action is, you go ahead and insert a beer tuple into the beers relation. Implicitly, the manufacturer value is set to null because it is not listed among the list of attributes for that relation, right? So you're only assigning beer, the new value of beer to name. You're not talking about the manufacturer, so the manufacturer is set to null. So these are the three parts, most important parts: the event, the condition, and the action. And then there is this intermediate part, which is allowing you to identify or reference the tuples that are being inserted. Okay, so that's the part that allows you to assign variables for the tuples that are being inserted or updated or deleted. So let's unpack this step by step. Okay, it's still not straightforward. So let's unpack this step by step. So let's start with the event, right? So the event is, in this case, after insert on cells. So instead of after, you can easily use before. So here we want to insert a tuple into beers after the insert on cells, but you can have it before as well, right? You can say, before the insert on cells, go ahead and do something. So you can do after, instead of after, you can do before. You can also do instead of, right? So you say, hey, I want to do an insert into X. I can, instead of doing an insert into X, I can do some modification and then do an insert into X or to Y. So instead of allows me to sort of prevent a modification from taking place and then change it and transform it and modify the modification and have it applied to a different set of relations. Now, instead of is a great way to execute view modifications. Okay, so let's say I have a modification to a view, and I say, go ahead and insert this tuple into a view. This tuple, I can take this tuple that's being inserted into a view, translate it into tuples that need to be inserted into the base relations, and have those be executed instead, right? So instead of allows me to execute or handle view modifications in a more elegant manner than relying on the database system. Okay? So it can be after, before, or instead of. These are the three sort of options. And then it's either insert, delete, or update. For insert and delete, it's usually just insert on cells or delete on cells. For update, it will be update of table on attribute, right? So you can say I can also do update on blah, but here I can also be more specific. I can say update of table name on attribute is a more specific way to talk about an update. So I'm saying that the update must be touching these attributes. So that's more powerful than simply saying an update on cells. Okay, so this is a way to be more specific about the type of update that's taking place. So that's the event. Any questions about this so far? Okay. Then you have the middle part, which I will go in reverse order. I'll start with for each row and then I will talk about referencing. So the way to execute triggers, so remember that you have, when you are having an insertion or an update or a delete, you often do multiple things at a time. You may insert 10 tuples at a time, you may insert 1 tuple at a time, or modify 10 tuples at a time, 1 tuple at a time. So in any case, there could be multiple things that are being modified. Now, the for each row construct basically says, for each of the things that you're modifying, do some action. If you don't have the for each row construct, then it means that you're treating the entire set of modifications as one set of tuples and you apply an action for that one set once. Okay, so once again, the for each row basically is a row level trigger. If you don't have for each row, you have a statement level trigger. The for each row basically, so if you have a row level trigger which is enforced via for each row, these are executed once for every modified tuple. For every modified tuple, you execute something once. Statement level trigger execute once regardless of how many tuples are modified. Why would I want both of these cases? So let's say I want to, for instance, for every tuple that's inserted into beers, I want to do some change to cells. Sorry, for every tuple that's inserted into cells, I want to do some change to beers. That's a for each row kind of case. That's a row level trigger. On the other hand, if I want to measure something about the entire set of tuples that are updated, let's say I want to check if the number of tuples that have been inserted is greater than 100. If I want to check that I can't do by doing each row. Right? I can't look at each row at a time. I have to look at the entire set of tuples at a time. So in that case, I would prefer a statement level trigger. Okay, we'll talk about examples of both of these. I'll clarify the differences in a little bit. But hopefully at least the high level idea that for each row is going to do something for every single tuple. Statement level is going to take the entire set of tuples and do some action for that. Okay? All right, so that's the for each row construct. Then there is the referencing construct, which is, so we've done for each, we're now at referencing. So an insert statement has either a new tuple, if it is a row level case, or a new set of tuples, which is a statement level trigger. Deletion, once again, has a old tuple or a set of tuples. Okay, so it doesn't have a new tuple. Update can have old tuples, new tuples, old sets of tuples or new sets of tuples. And the way to refer to these would be as new/old, row/table as something. Right? In this case, we have new row as new tuple. Okay, so if I instead had after update on cells, I might want to have new row as new tuple, old row as old tuple, right? That's totally fine. So that allows me to refer to the old and the new tuples and do some check that involves both of them. And between row and table, if I am using a row level trigger, then I would prefer to use the row. If I'm using a statement level trigger, I would use table. This table means the set of tuples that are modified. Okay, so if I have referencing new table as blah, that blah would refer to the set of tuples that are added. Okay, so these are the new tuples. Okay, any questions about this? Okay, so so the old row, new row constructs are used along with for each row. Old table, new table are used without for each row. This is when you are having a statement level trigger, not when you're having a row level trigger. Okay, so then we've done all of these. let's look at the condition. So the condition is any Boolean valued condition. This is evaluated before or after the triggering event, depending on whether you used before or after in the clause above. So this is fairly powerful because it allows you to check some condition of the state of the database either before you've gone and made any modifications, so before you've touched it, or after you made some modifications, you can go ahead and check something and then do some bookkeeping operations. So it's quite nice to have the flexibility of either doing before or after. And when listing this Boolean valued condition, you can refer to the old tuple or new tuples or set of tuples through the names that are declared in the referencing clause. Right? So here I have new tuple.beer not in something, and the new tuple is referenced via this referencing clause. Okay? All right, so we're done with the condition. Let's look at the final one, which is the action. The action in this case is simply inserting into beer's values new tuple.beer, but there can be more than one SQL statement in the action. In this case, you would surround by begin and end statements if there are more than one. But one thing to note is that all of these need to be modifications. Queries don't help, right? What would queries result in? They don't really result in any changes to the database. So queries don't make any sense in an action as part of the action statement, so we are really limited only to modifications to the database. So let's consider a couple of examples here. So the first example is I'm trying to find a list, given the cells relation, I'm trying to maintain a list of bars that raise the price by raise the price of any beer by more than $1. Okay, so if there is a change of a price of a beer by more than $1, I want to record that and I want to store that in ripoff bars. Note that there's no construct so far that will allow me to do this, right? In some sense, this is something that is allowing me to check, monitor an update that is taking place, look at the difference between the old price and the new price, and if the old price and the new price is greater than 1, then I want to record it. There's no construct so far that we've studied that allows me to do something like this. So once again, let's look at the final trigger and then we'll unpack it. So the final trigger looks like this. The event here is after update of price on cells, right? So I've gone and made an update of price. That's the one that I'm interested in. Any other updates I don't care about, right? After update of price on cells, I want to look at the old row as well as the new row, right? So I'm referencing the old row as old, new row as new, allowing me to talk about both of those tuples. For each such row, so each such price change, I want to look at the condition. Here the condition is new.price greater than old.price plus $1. So this is a raise in the price that is greater than $1. If so, I go ahead and insert into ripoff bars. The value is simply new.bar. So ripoff bars has only one attribute, which is the name of the bar. So when the price change is great enough, add the bar to ripoff bars. Any questions about this? So once again, it's a lot to take in terms of the number of keywords and the template, but like I said, I'm not, the goal of this is to not test you on this syntax, but more about trying to understand the underlying concept, which is there is this underlying event that takes place, and then checking the condition, and then doing some action to rectify. Okay, so here I am going to insert based on an update to cells. Okay, so I will cover this in the next class and then move on. Okay, so I'll see you on Wednesday.